Okay, we're back again for part 2 of a video demonstrating how to find critical points and possible points of inflection for a function. In part 1 we found the critical points of g. We found the critical points of g by taking the first derivative, writing it in factored form, noticing that it's defined everywhere, but its zeros are -2, 4, and 1. So the critical points of g were -2, 4, and 1. In part 2 of this video, we're going to find the second derivative. Its zeros will be the possible point of inflection for g. To that end, I think I want to do some rewriting for g prime. I notice there's this common factor of 2 that I can factor out of the third factor. That'll make the coefficient -1/2 when I factor out that 2. And I'll write down these factors again. Third factor becomes x minus 1. And to find the second derivative, I need to take the derivative of the derivative. Since there's 3 factors, that would be a little tedious, using the product rule for differentiation twice. So I'm going to choose to multiply these last 2 factors and rewrite that as a quadratic. X squared minus 4x minus x, collect like terms, and -4 times -1. Okay. So I think I want to start there. And now we can take the derivative of g prime. So I'm going to highlight that this is multiplication in between those 2 functions. And when I take the derivative of the linear factor, its derivative is just -1/2. I'll leave the quadratic factor alone. And now I'll add to that. I'll leave the first factor alone and take the derivative of the quadratic, which will be 2x minus 5. Okay. Ooh, that's a pretty long answer for g double prime. But upon observation, I can see that I can factor out a common factor of -1/2. And I'm not sure. Well, yeah, I am sure. Let me think about this. There wasn't a common factor for this quadratic and these 2 factors, because this quadratic is x minus 1 times x minus 4, and neither of those factors are listed there. So as I pull out this common factor of -1/2, I'm going to leave this quadratic alone. And when I look down here, I'm going to go ahead and multiply 2x squared plus 4x minus 5x minus 10. If you'd like to pause right here and double check my algebra and make sure that this function is equivalent to this function here with square brackets, do so now. And now we'll just go on and collect some like terms within the parentheses. Let's make sure 3x squared minus 6x minus 6. Nice. And to find the possible points of inflection, we're going to solve by setting g double prime equal to 0 and finding the zeros of g double prime. Okay. I may need some more paper here, so let me move some papers around. Okay. So we're going to set we know -1/2 is not 0, so we're going to set 3x squared minus 6x minus 6 equal to 0. And I think I'm going to factor out a common factor of 3 and use the quadratic formula to find the zeros. I don't think this will factor. There aren't factors of -2 that add up to -2. Okay, so pardon all the moving around here. Yeah, I just wanted to remind the viewer of the quadratic formula. So do recall that if we have an expanded quadratic with the coefficients a, b, and c, and we set that equal to 0, we can find the values of x that satisfy that second degree equation by using the quadratic formula. We can find the roots by using the coefficients of the quadratic. Okay, well, it looks like my values of a, b, and c are 1, -2, and -2 respectively. Okay, let's see if I can keep that formula in the frame. So we're looking for possible points of inflection. They're going to be the zeros of this polynomial. So they are equivalently the zeros of this polynomial. X equals opposite b, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay. If you want to pause here and simplify it yourself and then check your answer, that wouldn't be bad. Checking, I think I get 4 plus 8 all over 2. Okay. 2 plus or minus square root of 12 over 2. And I notice there's a perfect square under the radical. Okay. And so I'm going to pull this apart. 2 over 2 is 1, plus or minus. The square root of 4 is 2, and the 2's cancel. And we're left with square root of 3. So there's 2 possible points of inflection. And later, we would, to do some analysis, we would record the domain of G, which is all real numbers because G was a polynomial. And we'd look for possible twists to the left of 1 and to the right of 1. And we would check to see if our function g were concave up or concave down on each of those 3 intervals.